Alrighty. The best chapter of the book, Chapter 63, Alternate IO Models. I have been waiting for this the entire book. I've read all of that right there just for this chapter. There's been several references throughout the book about select pole, e-pole. Just independent of reading the book, obviously I've been doing my own research into e-pole and KQ and IOU ring, which of course KQ is not going to be mentioned here, I don't think, and IOU ring definitely not, because this book is very dated. But I feel like this will be a nice foundation for understanding select pole and e-pole that I can then build upon when choosing other, how would you say, alternative IO models such as IOU ring. Even though they're very different models, just having the context and the history and why, the reasoning why you might choose IOU ring over e-pole, for example. Yeah. So let's get into it. Alternate IO models. And I'm going to be doing a lot of the exercises and writing experimental programs as we go along here, because it's something I'm actually interested in. So I'm just going to go ahead and make my directory here, mkdir chapter 63. I'm going to do all this in C. So let's find our makefile name, makefile. Rsync. Actually, you know what? We'll just cp chapter 61. Oops, 61. Was it makefile and dot get ignore into chapter, was this 63? Okay, I'm gonna go into there, see what we got going on. Make, okay. Alrighty, let's begin. This chapter discusses three alternate, I need something to fidget with here. This chapter discusses three alternatives to the conventional file IO model that we have employed in most programs shown in this book. So the conventional IO model is open, read, write, close, and then you can do read V and write V, which are basically vector forms of read and write, to read V. So go back over here. So that would be the conventional IO model. Like, you have some mechanism for acquiring a file descriptor, and then you perform operations like read V, write V, and then if you're using sockets or other, I think there's three different ways of sending data on a socket with receive message, send message, and there's, I think, vectorized forms of those. And I think it's receive M message. Man to receive M message. Is that one? Yeah. So there's these M message alternates. There's I think this is the one that has the most flexibility, because it receives multiple messages on a socket. And then there's receive message itself. Then there's receive from. Yeah, these are the three that I was referring to. So send from, or send to, and send message, and then receive from, and receive message. That's 6. And then there's I think these are the vectorized forms of receive M message. It's called receive multiple message from a socket with a single system call. And then I think, is there even a vectorized form of this? No. I think that is the vectorized form. Okay, so you got all these different ways of doing reads and writes, and a lot of them involve having a buffer in the user space, the process user space. The virtual memory address space of the process has a buffer that you put data into, and then you make a syscall that says, hey, here's the buffer I want you to read from to write this message out onto the network or to a file on a disk or whatever. And in doing so, the kernel then goes through your buffer and copies all that into kernel memory and then sends it out to a network interface card or to a hard drive controller or something like that. So there's a lot of copying involved in there with the kernel copying data from the user space into kernel address space. There's also the syscalls, which involve context switching in between the kernel, saving off registers, monkeying with, different values. Basically, the execution context of the thread that's executing has to be saved, and then you have to, jump into the kernel or do a trap or a syscall instruction into the kernel. Then the kernel, does its stuff and then has to do the inverse to restore the execution context of the thread. So like all that work is just like a lot of overhead. What would be nice is if you could avoid some of that overhead. And techniques like IOU ring are the most performant way because you can basically tell the kernel, hey, I'm going to set up these buffers in my address space, or we're going to coordinate on setting them up. And I'm going to put data into a send queue, and I'm going to read data off a read queue. And we're just going to coordinate using memory operations on the memory that's in that block of my address space. And that doesn't involve any syscalls. I think IOU ring has like two modes where one mode you can call into the kernel to get it to actually do the work. And then the other mode you spin up a K thread, a kernel thread that monitors the memory and like takes actions independent of you making syscalls. So very high performance, but we're not going to be discussing that this chapter. We're going to be discussing what is typically, I think, referred to as event-based I/O or asynchronous I/O, I think you might call it. There's like multiple different kind of like terms that are thrown around that, to be honest, I don't really have full clarity on. The precise technical definitions of these things. I mean, obviously you can kind of extrapolate what they mean from the names themselves, but asynchronous I/O would be I/O that isn't your traditional read and write where the read and write will block, but you can already give the non-blocking flag to the file descriptor when it's opened or to the read and write operations themselves. So non-blocking I/O does not require the use of any of these techniques. You can do non-blocking I/O already. Evented I/O, I think that's probably a better term for it, because when an event occurs, like you receive a TCP segment, some bytes to be read from a buffer, then the kernel can let you know about that event. That's an event that occurred. It can let you know about that event using one of these mechanisms. So I think event-based I/O is probably a better term. There's one other term I'm forgetting. It's like on the tip of my tongue. When discussing alternate I/O models in Linux, the terms event-based I/O and async I/O are thrown around. What exactly do these terms mean, and how are they meaningfully different from each other, and what other terms are used to describe alternate I/O models? Let's see what AI says. Yeah, I don't need a full walkthrough on this thing. Event-driven I/O. Tell me when I can do I/O. Okay, that's the select epoll poll KQ. Asynchronous I/O. Okay, that makes sense. So what we're discussing here is asynchronous I/O, or is event-based I/O. Asynchronous I/O would be like hey kernel, you do the IO and then let me notify me when it's finished. And so IO uring is actually an example of that. And then this AIO, POSIX AIO, which basically died on the vine. It's not really like a thing that's in use from what I understand. And Windows IOCP. Okay. So IO uring is asynchronous IO, even though people call it epoll, select poll and epoll as asynchronous IO. Those are event driven IO. You would still do read, but you can do the read as a non-blocking. Non-blocking IO is the other. Those are the three things: non-blocking IO, event-based IO, and asynchronous IO. So I think I'm getting a better mental model for it now. So non-blocking is just the fact that the operations that you're performing do not block. Event-based IO is when the kernel lets you know that you can then perform an IO operation that may or may not block. And then asynchronous IO is when you tell the kernel, hey, I want you to do these IO operations. Let me know when they're completed. I'm not going to wait around for you. Yeah, it's not true async IO. It is event driven. I think just knowing that it has an E in the name, epoll, it's kind of easy to remember that it's event driven. It's not async in the sense that the kernel, you can't just tell the kernel, hey, do this thing and then I'll check back later. Let me know when it's done later. It can be blocking or non-blocking. Yeah, read returns E again. You retry it later. So that's blocking IO, non-blocking IO. IO multiplexing. That's a good word for it as well. IO multiplexing because you have a single thread that's doing multiple forms of IO. Signal driven IO. We haven't even gotten into that. And then true asynchronous IO is AIO or IOUing. Go runtime netpolar. Sync versus async versus blocking versus non-blocking. So blocking is the thread basically gets descheduled off the CPU. Non-blocking, this is call returns immediately. You get like an E again, or you get the data if the read complete. Synchronous is you perform the IO. Asynchronous is kernel performs the IO. I think that's where the terminology is a little bit muddy in my mind, because in my mind, synchronous versus asynchronous has nothing to do with the kernel. Asynchronicity is like synchronicity is that there is a ordering of events. Like this happens before. Whereas asynchronicity is that there is no ordering of events. That the ordering of events could be arbitrary. And I guess you could. There's multiple. I've wrestled with this term synchronous and asynchronous for like my entire career. Like if you think about it from like a hardware perspective, like synchronous is like falling edge, synchronicity in a clock, like in a CPU like clock or a square waveform generator. Like you can synchronize the operations of an electrical circuit based on the rising or falling edge of the clock, and that synchronizes like what's going on in the circuit. So that's one form of synchronization. Asynchrony is just electrons are flowing regardless. So synchronicity takes work. Asynchronicity is just how the physics like wants to behave at a fundamental level. Like things are just happening independent of each other all the time. When you coordinate and you order things, then there's a synchronicity that's applied to it. And so I take that idea of like synchronicity, asynchronicity from like hardware and try applying it to software. I found like people in software kind of like mean something different when they say asynchronicity than what I mean. Like most of the asynchronicity stuff that I see in software is based on like networks and messaging patterns. Like request response is asynchronous. I submit a request, I wait for a response. That's synchronous. Whereas asynchronicity might be like I send a bunch of UDP packets and then go do something else, and I don't have to wait for them, or I could optionally wait for them and they come back in any order. Like that's like asynchronicity on a network level. But when applied to I/O, I think asynchronicity means like I hand the kernel a bunch of work to do, and then at some later time I'll check in on it and see how it's going. So blocking I/O, I perform it. I'm notified after the completion. When it says I perform it, the kernel is really still. That's why I don't like this terminology. I'm just gonna skip this because the kernel is always doing the I/O. You're not reading and writing bits to the networking cards and the hard drive controllers. Like most of the time, you're not doing that. So like when it says that, oh, you're doing the I/O. Actually, no, the kernel is doing the I/O. But blocking just means that you submit the individual unit of I/O to the kernel, and then you wait, and you are pulled off the CPU while you wait. And then when you're done, when the I/O is done, then the kernel it puts you back on the CPU and lets you know that the I/O is complete. So it's a very simple model for I/O, and involves a lot of cost and copying buffers in and out of the kernel and user space, context switching, and the penalty of sleeping your process and unsleeping it. Non-blocking, basically, it's the same exact model as blocking, except you have the non-block flag set on the file descriptor or on the I/O syscall itself, and it always is going to complete immediately. It means that you're not going to get pulled off the CPU. So that's the difference between these two, is that this one you get pulled off the CPU, this one you are never going to get pulled off the CPU. Event driven, so that's what we're going to be discussing mostly in this chapter. Basically, you're monitoring file descriptors, and the kernel lets you know when those file descriptors are ready to perform an I/O that you can then perform either blocking or non-blocking. And then the last iteration, which is async I/O, which is you put a bunch of I/O operations. In the case of I/O ring, you put a bunch of I/O operations into a ring buffer and then you let the kernel know, hey, it's time to do work, or you have a K thread working in the background that does the work automatically. epoll plus non-blocking. So event-based and non-blocking for 20 years. Then IOU ring arrives, change the game. So I've seen myself go use the epoll, non-blocking sockets, runtime scheduler. Okay, that helps. Readiness model, epoll reactor. Completion model, IOU ring proactor. Okay, that really helped. Clarifies some of the terminology. So now we now understand that blocking and non-blocking IO are different axes than event-based IO, which is like just notifying when you can perform a blocking or non-blocking IO operation. Blocking and non-blocking just means whether you're going to be pulled off the CPU or not. And then finally, asynchronous IO is this wholly new model where you hand the kernel the IO operations to perform, and then you check back later to get notification of their completion. And with event-based non-blocking IO and asynchronous IO, both of those models, you are not pulled off of the CPU. I guess you can have event-based blocking IO. Yeah, event-based non-blocking IO, any non-blocking IO and any asynchronous IO are both going to be not pulling you off of the CPU. Your process is going to remain running on the CPU. Okay, I think that clarified things. Sorry about that. I needed to like do that up front just to kind of get the terminology straight in my head. Okay, now they have this new concept, IO multiplexing, the select and pull system calls, signal-driven IO. So we haven't even talked about that, but I guess we're going to have some of that in this chapter. And then the Linux-specific epoll API. Overview. Most of the programs that we have presented so far in this book employ an IO model under which a process performs IO on just one file descriptor at a time, and each IO system call blocks until the data is transferred. For example, when reading from a pipe, a read call normally blocks if no data is currently present in the pipe, and a write call blocks if there is insufficient space in the pipe to hold the data to be written. Similar behavior occurs when performing IO on various other types of files, including FIFOs and sockets. Disk files are a special case. As described in chapter 13, the kernel employs a buffer cache to speed disk IO requests. Thus, a write to a disk returns as soon as the requested data has been transferred to the kernel buffer cache, rather than waiting until the data is written to disk, unless the OSync flag was specified when opening the file. Correspondingly, a read transfers data from the buffer cache to a user buffer, and if the required data is not in the buffer cache, then the kernel puts the process to sleep while a disk read is performed. The traditional blocking IO model is sufficient for many applications, but not all. In particular, some applications need to be able to do one or more or both of the following: check whether IO is possible on a file descriptor without blocking if it is not possible, monitor multiple file descriptors to see if IO is possible on any of them, We have already encountered two techniques that can be used to partially address these needs: non-blocking I/O and the use of multiple processes or threads. We describe non-blocking I/O in some detail in section 5.9 and 44.9. If we place a file descriptor in non-blocking mode by enabling the O non-block option, open file status flag, then the I/O system call that can't be immediately completed returns an error instead of blocking. Non-blocking I/O can be employed with pipes, FIFOs, sockets, terminals, pseudo-terminals, and some other types of devices. Non-blocking I/O allows us to periodically check or poll whether I/O is possible on a file descriptor. So the problem with just doing regular non-blocking I/O is that you're constantly polling and checking in on it. Whereas the select allows the process to get pulled off the CPU if there's nothing to do. So select, you're still getting pulled off the CPU. That's interesting. For example, we can make an input file descriptor non-blocking and then periodically perform non-blocking reads if we need to monitor multiple file descriptors. Then we can mark them at all non-blocking and poll each of them in turn. However, polling in this manner is usually undesirable. If polling is done only infrequently, then the latency before an application responds to an I/O event may be unacceptably long. On the other hand, polling in a tight loop wastes CPU time. In this chapter, we use the word poll. I feel like I need to write a testing harness here and then kind of gradually step through these different models. So let's pull up a little browser here for Excalidraw. And we're going to kind of play with some ideas here. So we're going to have our app thread. Actually, let me delete that. Can I just double click on this? There we go. App thread. So this is the guy who needs to do some type of like I/O operations. And I think the way that I'm going to structure this is just going to be like an I/O server. And it's going to need to perform multiple. So the I/O server, it's going to listen on a port, and it's just going to like, let's just make it like an echo server. No, because we need to have it be blockable. Trying to think how we would do this. Because most I/O operations are going to fit into the buffer. The buffers in the kernel, or the buffers, or the user space of the server. So what we can do is we should be able to give it a signal to halt, and then give it a signal to resume. I think we can do that by just doing Control-Z. But if we want to do these, do we want to do these connections? So this thing's going to make multiple connections to the I/O server. Let's change this to be both directions. And so it's going to have multiple file descriptors. The thing is, like, each one of these connections I want to be able to halt individually. So I think I need to have 3 threads, or a number of threads. Let's do a general threaded server here. So I'll just call this IO server.c. Bind and listen to socket. Enter loop. Oh no. Spin up thread to handle accept, and then main thread blocks on standard in instructions. Start standard in instructions. That's the basic idea of this server. So to bind and listen to the socket, so func bind and listen, and we'll give it a port. We'll say port int port, and it's going to, I'm writing go, I know, int, it's going to return an integer, which is the file descriptor. Okay, turn -1 here. Okay, oops. Okay, so here we can say, hey, bind and listen, and we'll just default to port 1, 2, 3, 4, 5. It's fine. Actually, you know what? I'll do a parse on the argv. So arg assert, we need to include assert.h here, and here we're going to say assert, and our argc is going to have a length of 2. And then here we're going to say a to I. If I go here, man a to I, you give it the argv sub 1. That's going to give us back int port. And then a to I can fail, so a to I return. Let's see what return here is. The converted value or 0 on error. Okay, that's a bit strange to have 0 be an error, because you, I guess, okay. Say assert that port is greater than 0. Okay, so now we got a port. We can pass it in here, port. Bind and listen gives us back the int fd. And we need to forward declare this up here. And then we don't need that anymore. And then here we're going to say start dispatch. Just call it that. Give it the FD. And this thing's going to return, it's going to be a void. Yeah. So we say void start dispatch. And it's going to take in an int FD. And then here, it's just going to wait there with the FD. Actually, it's going to return an integer here. Assert that ret is greater than or equal to 0. Oh, what's going on here? It's going to be dispatch here. There we go. This needs to return 0 for now. FD is an integer. There we go. Okay, and then finally, main thread blocks on standard in. So here we're going to say handle input. And up here, there's going to be a void handle input. Okay, that's the overall kind of game plan for this process here. All right, binds and listens to a socket here. So the first thing will be creates socket, binds it, and listens. Okay, so now we man up socket. And here we need sys socket. Sys socket h. I need to get back over here, put another semicolon, get that to fix there. All right, so we're going to call socket. The domain will be the internet domain. Domain type protocol. So inet type will be stream, and the protocol will be 0. Now it gives back our int fd, which will then return fd. We say if fd. Actually, let's just assert this as well. Fd is greater than or equal to 0. The domain I need the actual domains. Well, this is gonna be sock stream here. Sock stream. And then this is, I think, AF inet, something like that. Yeah. Okay, that worked. We got a file descriptor now. So now we need to bind it. Man bind. So I think we just say we bind our FD to some adder as a reference, and len of adder. There we go. That's going to give us back int ret, and we just assert that ret is greater than or equal to 0. And then our bind, let's see, sock adder. I guess we can just say up here, struct sock adder is adder, and we're going to initialize it to all zeros. I think I'd do it like that. Len will be size of. And then adder in here, we got to give it some fields, right? So I think that's where you say it's like a v4 adder, right? Versus a v6 one. v4. Let's get out of here. I think it's sock adder v4. Adder 4 v4 adder v sock. Generic socket address. This is all socket.h. v4. Is there a 4 anywhere here? Okay, I don't want any of that. All right. Okay, it's gonna have adder in it somewhere, right? Oh, include bits sock adder.h. How do I find the v4? It was sock adder common. Sock adder storage. Okay, well, let's see where this sock adder common goes to here. Well, let's look for adder here. Here it is. Alright, so we got our, that's a Unix. So I want a sock adder underscore. Let's get out of here. Alright, buffer delete. There we go. Underscore IP? Or IN? No. UN? No. Define is for Unix domain socket. I want a example. Let's just ask ChatGPT on this one. Give me an example of binding to a IPv4 TCP port. Okay, we call socket, inet checkstream. Okay, yeah, we definitely want to do this as well. So we say set sock opt, give it the file descriptor, say sole socket. Sorry. Set sock opt, FD level opt val length. Okay. So you say FD sole socket, SO reuse adder, give it the pointer to the option and the size of the option. And I think that's it, right? Yeah. And then here, we're going to assign that to ret, int ret. Then down here, we don't need to redeclare that. And we'll just do our same assertion here and our struct opt. What is it called? What is the opt called? Just an integer. Okay. Int opt is equal to 1. Alright. So that'll get us to reuse the adder. That's a good addition, I forgot. Yeah, it's socket adder IN, but for some reason I'm not pulling it in. Maybe because I need this ARPA inet. Hey, there we go. Okay. So we're going to initialize. See, it uses this syntax here with the 0. I'm going to do it like this, where I say sin family, dot sin family, sorry, dot sin family is equal to AF inet. And then sin port is going to be the H2 ends of the port, and then sin adder dot s adder. Can I do that whole thing there? H2NL in adder any. These commas? Okay, they're commas. There we go. So initialize the whole thing. And then we call our bind. But we have to assert this pointer type, that's right. Or we have to cast it, sorry. Struct sock adder pointer. Yep. Makes sense. And then we do our listen. This could be rets as well. Listen on the file descriptor, and we just give it like a 16. Okay, and then, yeah, printf, why not? That means that we need my standard IO H. Okay, looks good. Oops, jump. Okay, we're building. So we got our thing listening. Then we call start dispatch. So it's going to use pthread. I'll get out of this now. Man pthread create. So it's going to call pthread create. And because I'm doing asserts, I'm just going to remove this and say it's a void. And I'll just do the asserts inside the function itself. Okay, so pthread create. We need to create our thread structure, which needs to hang around for a while. So we can heap allocate it, or we could stack allocate it and then pass in a reference to it. I like that it would be stack allocated, but that requires a little bit more work on the caller to create a what would this be, a thread, pthread T, and we pass it in here, T. Okay, this takes in a pthread T pointer called T, and then we're going to say, okay, you already got your pointer, just pass it in here. You need to put a semicolon here, and this is not going to have a return. It's going to be pthread create T. The adder structure, which can be null, don't need anything there, and then the routine itself, which will be dispatch, but it needs to be bound to the file descriptor, which I'll pass in as an argument, and this will need to be a pointer like that. I think that's how you do it, right? Maybe I can just pass it in as a function itself. All right, so the arg is a void star to the argument. Okay, how does arg work here? I don't really care about the attributes. I want the arg. Where's the pthread create? Okay. Here it is. A reference to, yeah, you'd have to do a reference here. Makes sense. But this would be a reference to tinfo tnum. And tinfo is a bunch of stuff that I don't care about. So I'm just going to give it a pointer to the FD. And the FD, no, because that's stack allocated. I could just say void star FD here. So I needed the pthread include, just pthread.h. I'm gonna pull out, this is all the stuff that's like common C stuff. This is threading stuff. This is socket stuff. All right, so now we're down here. Dispatch needs to be declared before this. That makes sense. The thread that accepts connections and dispatches in. So here we're just gonna say while true, or I see this more commonly, forever, do accept file descriptor, and then a bunch of socket information I don't care about. So can I do file descriptor null? Will that work? No, because I don't care about the stuff right now. Null. And that gives you back what? Gives you back an integer, which is a int fd. We say client fd. And then we assert the client fd is greater than or equal to, we'll say 3, greater than 2 here. Then here we're going to do pthread create in this loop. Yeah, I can see why this doesn't really need to be its own thing there. We'll just do that. That simplifies things a little bit. Oh, does this have a certain signature it needs to be? It has to return a void star here. And we'll just return null. Okay, it's still complaining. Oops. It says incompatible function pointer types void star int. Oh, this needs to be a void star. I need to cast it to an integer. Void star fd, or we'll say arg, because pthread create says it's the arg. Then here we say int fd is equal to arg if it was casted as an integer. Cast a small integer type int from void star. I don't know what to say there, bro. Unsigned log to parameter of type pthread t star. Integer to pointer conversion. Okay, oops, sorry, I didn't mean to do that. Let's ask AI. Say, how do you convert a file descriptor to a Thread arg void star. Okay, int pointer t and then to an int. Okay. Unix standard.h now. Pthread standard int.h. And then over here on the calling side, we do the inverse, which is int pointer t. Okay. So we say fd goes to an int pointer t, which goes to a void star. Oh, and then this needs to be a reference here. True, because I deleted that function that wasn't really helping us. All right. Looks good. Oops. Damn it. All right. Just messed up that. Chapter 63. Okay, make IO server. There we go. Okay, so we got our dispatch going, or we got our dispatch being called, right? No, we got our, wait a minute. It's going to create the thread to dispatch. It's going to spin forever and do is accept. Okay. It's going to accept, it's going to pthread create its own threads here. This one I'll just call handle call, or handle con. And this will also be a file descriptor, but it'll be the CFD. So instead of handle input, we need handle con, which we handle con. Okay. It's going to do its same thing here. Convert its arg to an FD. Okay. Alright, so that sets up all that stuff. I'm just going to say for testing here, I'm just say printf if I can get this thing out, we'll say and here we'll say it's just going to immediately exit, that's fine. Okay. And then we have a handle input, which is going to read from standard in, read line, I should say. Use command read to modify some sort of state that is shared with the threads. For now, I'm just going to pause. And we can do our pause up here too. And I'll just pound include if we man up pause, That doesn't actually. Unix standard.h. Okay. All right. Let's make build IO server. Okay. Yeah, I need to say what port. Okay, it's listening. And if I do just say quick netcat, connect to local host 12345. Yep. Cool. All right, so we got a basic threaded server set up here. It's going to be our IO server. And what I wanted to do is I wanted to have some type of shared state with these threads so that I can control their operation via standard in. So I'll perform, we get the read loop going here. So I'm gonna read from standard in into my buffer standard in, which is, sorry, standard in file no buffer, sorry, pointer to buffer, size of buffer, and we'll just make our buffer be a character array of size 255. Why not? Why would we do 256? Why not? Okay. Actually, no, they'll just do 80. Not gonna need much more than that. We're gonna do our read. And we're gonna say if, or say n for ever do, don't need the pause anymore, int n, read returns n, right? Yeah, size of t, s size tn, and then we say assert that n is greater than or equal to 0, and then we can say switch on buff case foo statement requires expression of integer type. Char 80 is invalid. Okay. We'll have to do a conditional here. If stir equals, stir n equals, stir compare, CMP, stir n CMP. Yeah, there we go. Let me put the man page, man stir n CMP. You give it the 2 strings and the size of the string. So it'll be, wait a minute. Const char s1n, s2n, size n. Stir compare function compares 2 strings, locales not taken into account. The comparison is done using unsigned characters. Okay, stir compare returns an integer indicating the result of the comparison as follows: 0, negative value if, yeah, positive value. Okay, so we can do, where are we at? Down here, handle input. The second will be buff, which we pass as just buff. Actually, I don't even think I need to pass that as a reference because it's already a reference type. It's char star basically. All right, and then yeah, if I don't think there's a difference between a reference to the char star. I guess it would give you the memory. I think it's the same. I think ampersand buff and buff are probably the same there. Let's do printf and say, hey, and I'll do this up here because I don't need to have it once. New line. We'll say ampersand buff percent %p of ampersand buff here. And if we do just buff, I think it's the same. All right. What the hell happened there? Okay, in here we're gonna say got command foo, new line. Okay. String.h. Okay. Well. Yeah, you see the pointers are exactly the same. So it doesn't matter if you take a pointer to an array or just pass the array itself because it's already a pointer. It's the same bit of memory. It's a weird semantics of arrays. C's arrays are just weird. They shouldn't even be a feature in the language, in my opinion. Or they should have been done differently. Okay, so we got our server running, and if I say foo, got command foo, bar, got command foo, what? The hell? Oh, is equal to 0, I should say. So make foo bar. So why does foo not come in? Because it's foo new line? Probably. So I'll just add the new line here. make run foo bar bar. Okay. Okay. What is this thing up here? 127 MP thread. What the hell is that? What the hell is that? There's no way. Oh, it's just a glitch. Vim glitch. Thanks, Vim. Okay. What's next? Oh, we need to decide what sort of state we want to be sharing with the threads, and also like a scheme for guarding access to it. Ugh. So I think it should be file descriptor indexed array. I think that's the way that we should do it. And the array should contain Alright, so we should have some type of like file descriptor indexed array. The array should contain like, what is the max file descriptors for a process? Here we go, get our limit. We'll just stick with the soft. Do we want to use a global to communicate? Or do we want to pass a reference to the threads? We're already passing our file descriptor to the thread, which you can use to compute its offset into this thing if it's a known location. I think a global would be fine. Problem is that it needs to be initialized early. So here we're going to say an array of something. We'll just say a char array. What do we want to call this? Con state. And we'll just say it's an integer array. Con state. Sorry. let's say it's an integer pointer const state, and currently it's equal to null. And then here, we're going to basically allocate the memory for it on the heap. So malloc. But first we need to discover our limit. So we're going to just call a function called init con state. And then here we'll have our void init con state. It's gonna do its malloc, but before it does that, it needs to do this, which is to get the R limit on the number of file descriptors, and then R limit cur is what we're gonna run with. So now we're going to malloc up size of integer times the r.rlim cur variable has incomplete type struct r limit. I need this header resource, this resource. Okay. Then here we're going to assign that to con state. It's equal to that. Maybe we say con state like this. There's no reason it needs to be capital. Oops. Give it a little. Yeah, we can make this static too. I'm fine with it being like this. You knit it up front. So you knit con state. It does a malloc. I think malloc is guaranteed to be 0 initialized, right? Man malloc. Memory is not initialized. Okay, so we gotta do a mem copy, I guess. How do you initial malloc memory to zeros idiomatically in C? It doesn't seem like I needed to do this, so I'm gonna punt on that. Oh, you can use calloc, okay. Yep. Okay. Calloc. So instead of malloc, we're going to call calloc. So calloc has a different signature. So it has a size t, but it also has an n. Calloc function allocates memory for an array of n elements of size bytes each. Return a pointer to the allocated memory. Memory set to 0. So I think what I want to do is this malloc. I think I want to do it like this. Instead of doing the arithmetic, pass those arguments in. Okay. Looks good. So our connection state is now initialized, so we can then, oh, we also need a set of mutex. So we need a pthread mutex t. We'll call this mu. Yeah. Did I do it? Do I need to initialize that? Sorry, pthread mutex. How do I get docs for pthread mutex? Init, is that a init function? Man, pthread mutex init. Okay, here we go. So we gotta initialize the mutex as well. So we just say, hey, pthread mutex init reference to mu. I'll call this con state mu. Con state mu. And then what is this pthread mutex adder t? Search for under init. Initialize the mutex object pointed to by mutex according to the mutex attributes specified in mutex adder. Mutex adder is null, default attributes. Okay, so I can just use a null there. Null. Okay. So when we read here, so I think what I need to do is say there's block and unblock commands. Can I use scanf on this, maybe? Maybe I should use scanf. Scanf. Format input, like, but read from a file. Fgets, get line, and then parse them later with scanf. Stir too long. You could use scanf, right? Okay, so use getfs or fgets. I'm gonna use scanf like they're saying in the docs. Okay, let's do that. So line command. So here, instead of doing read, we do. We already did our read. So I'm gonna skip past that. scanf line. Okay, let's try that. Then we cert is equal to 2. Okay, that's gonna crash the program, so I'm not gonna assert that. I'm gonna say if or continue. Line will be buff. Command and value should be like this. Yeah, I kind of do like this being line. Line. This will be command, will just be, I guess, 7. And this will need to be %d. Okay. If it's not equal to or if it's not equal to 2, then we add a bad command and we continue. And then we say switch on value. Value. No, not value, command. So we can't do that. We have to say if block is the command. We'll just say 8 here for size of command. So we %d, which will be value. Okay. Chapter 63, make, build IO server. Here we go. Bad command, but I can say unblock 12. Yep. Block. If it's a block 2, it says unknown command. Okay, everything's working. So here, instead of printing this stuff out, we're going to actually take out the mutex. So we say pthread mutex lock, and we give it the pointer to the con state mu. And because this is used after that, I have to move this down. below here. Okay, so now we can then unlock it. Do the same thing here. But here we're going to say con state of fd, which we value is equal to what? So block is going to be the default, which will be, no, unblock will be the default. So block will be like that. Okay. Oops, make. There we go. Okay. So now we have to do some testing. We also should print out like we should have a command that prints out the current. Let's call this print. And this won't, this will need to take out the mutex, but I also want to like, I guess what I should do is list the file descriptors. So I think what I want to do is list out the file descriptors that are currently open for the process, and then list out all of their states, which require taking out the lock. C code to list current active FDs in a process. No easy way like a lever. Can you write me a function that abstracts this operation? Okay. So this will go up here, maybe here. I don't know why I need that, but who knows. go ahead and fix these. Oop. Don't need that. Actually, just move all these up here. Okay, so we got our function here for each open file descriptor. So it opens the directory. No, I don't want to do a brute force scan. Oh, that's interesting. Let's just do a Linux specific thing. So open that. We read all. We convert A to I. Skip the directory after used by opendir itself. That makes sense. We call our callback. With the argument. I don't think we need the argument. What do they use the argument for here? Yeah, they don't even use it. So let's just make sure this is here like this. So now we have our FD iter CB. Okay, so here for each one of these file descriptors, we want to acquire a lock. So down here, I do need a function that does that. So print for each open FD. This would be a void star? Yeah, or just a void print FD state given the int FD, and we'll just say take the lock and unlock. This would be FD, and we'll say, hey, can you add a check to make sure the FD is a socket? I'm not gonna use that. I'm gonna. Okay, yeah, I will. Okay. Now I need some more stuff up here. Obviously, these are good. I never need these for some reason. String.h, got it. Unix standard.h, fcntl, sysresource, sysstat. That's what I want. Okay. No arg here. There you go. We'll say %d and has the connection state %d. New line. Like that. And we'll do FD here. There we go. Okay, and then down here we need to say the for each open. This needs to be print FD state. For each open socket, print socket state. I'll change this to be print sock state. And then up here for each open sock. And then we'll do our little check. So he does open dir, read dir, skip that, continue A to I. Then we do this check after our check to see if it's a directory. Yeah, here we go. I don't like these, so I'm gonna fix them. Same thing here. Okay, is socket FD now has to go above this, like that. And then finally CB. How does this thing keep on getting the... Oh. We'll say if not, continue. I like that better. Yeah. Okay. Let's go ahead and make that. Do our build. Pull this up. Print. Bad command print. Okay, so now I have to go back here. Why is this freaking out? Oh, because it doesn't have a digit here. Less than 1. Change that. Print. There we go. So we got socket 3. Okay, make that, and we'll say print. Oh, it's because I have a not here. If it is listening socket, we continue. Also, unknown kind of want this thing to have the command. So this will be line. We'll do the whole line, why not? Okay, make, run, print, nothing. But if I go over here and do my NC handling connection 9, print. So I got 9, and I can say lock 9. Unknown command lock 9. Oh, sorry, block 9. Print. Let's say or B. This would be U. And this will be P. To make some shorter names for it. P. Alright. Make, run, connect, P. We'll say block 9, P. And we say unblock. We say block 9 again. P. Unblock 9, P. Yeah. Looks like it's working. Okay, so we have this integer that we can associate with socket file descriptors now, or any file descriptor on the system, but we print out just the socket ones. So now that we have that, we can communicate an integer between our command interpreter and the state of the socket itself. So that would be up here, handling connection. So I kind of feel like if it is, we want like a read with a timeout. In raw syscalls on Linux, is there a read syscall with a timeout? Yeah. What about for socket? Socket only option, here it is. So we set the socket option to have a timeout. So we go up here. Before we handle the con, is it, I think we can handle it here. We can keep it there. The time val 5 seconds. I think we should do it 1 second. And then we do that. Then we perform a read in a loop. E again, or E would block. So forever. So we're not going to be hugely hammering the CPU. We will be hammering it a little bit because every second is going to wake up. But what we'll do here is we'll take out the mutex, read our current state. So we should just have two functions to get and set as well as print. So get sock state, which returns an integer given the FD. And this will just be int state is equal to, oops, let's go back here. We'll say int state is equal to that, return state, and then we'll have a set sock state, and that'll be int state here, which I think I can do it like that. And then this will just be like this state. Why is that? Okay, whatever. And then down here, instead of doing this stuff, I'm just call set sock state FD value FD 0. And this would be FD1. Is it FD? It's value, sorry, value. 1, value. Value. So print sock state does the same thing. Alrighty. So let's go to our handle con. So we're going to get sock state for the FD. Just give us back int state. I think it was called get sock state, right? Get sock state, but we need to move this handle con down. And this thing as well, dispatch needs to go down. Okay, so handle con and dispatch need to go down. Below all of the sock state stuff. Like here. Does that fix that? Yeah, it looks like it. I hate that there's like a linear ordering to all this stuff. Let's see. Okay. Handle con, we know get sock state. We then perform our read into a buffer. So if we hit EOF, we're going to return, or you say break. Can I just say EOF here? That should be 0, right? EOF is -1? I don't know about that. Man to read. where's ELF here? Return value. On success, the number of bytes read is returned. 0 indicates end of file, and the file position is advanced by this number. So 0 is just known to be ELF. Okay. 0 here. And then we say else if. We can just say if. We need to do that. If n is equal to e again, or e would block. E again, the file descriptor refers to a file other than the socket that has been marked as non-blocking. Hold on, let me reread this. The file descriptor FD refers to a file other than a socket that has been marked non-blocking and would read, and the read would block. See open. That's not us because we are a socket and we're in receive timeout. So E would block maybe? Okay, I'm just gonna print out the exit code. How about we do this? If n is greater than 0, we just do a continue here. If it's equal to 0, we break. If it else, we just printf the read of fd returned that. So we say fd and rets, or n. And we continue. Okay. I think that'll work. Let's do make build IO server. Sorry. 1, 2, 3, 4. And let's do nc localhost read -1. It's doing -1s each second. So if we do over here man to read, so I'm gonna do that. -1. Oh, error number is set to indicate the error. So I have to do a p error. Okay, let's do %d here. Do I get the string representation of error? No. Stir error no. Okay. Come on, get out of here. Get out of there. Right, please. There we go. Make. There we go. Resource temporarily unavailable. I just want to map back to the symbol names like E again. Is there no library function that does this. Okay. Well, what we can do is we can roll with that. It's fine. It's not reentrant, but who really cares? Error no. I'm gonna put error no here. Should be %d error no. That I hate error no. Okay, 11. Resource temporarily unavailable. Man to read. The fuck is this? Let's just do like E again here. E. And then maybe go to definition. Oh, it is E again. Okay. So if it's E again, we just continue. So state blocking would be like if state. So I need to do one, then we're just gonna sleep for 1. Let's do that. Make bam NC. So handle connection 9. What if I say hello? P. Why is it getting E again? Oh, do I have to fill up the full buffer? I don't want to write the whole buffer. What I want to do is say 1, 2, 3. I want the new line character here as well. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this would be 14. So we set our socket state back to read mode. We then do our string copy into our buffer. We then write that out to the file descriptor, and then we say, hey, we wrote to the file descriptor. Here's our return, our error node, and everything. This has a redefinition of n. So I'm going to say int n goes up here. Oops. Then this becomes like that and like that. Okay. And now we don't need to continue on that or this, but we do need a break. And I'll break at the default, because why not? Oh, this is not going to break the switch, but we want to return, I guess. Be the easiest way to do that instead of doing a go-to. How do I set the state to 2 though? I have to do like a write command. So let's go ahead and copy all of this and paste it here. Now I'm going to say, hey, you're going to be write or W, and you're going to set the socket state to 2. Okay. Write to 9, got back 14, resource temporarily unavailable. So maybe we set that right back into blocking mode. But we already set the timeout stuff. Yeah, it should be in blocking mode, just with timeout. So why did we get back resource temporarily unavailable? If I do W here and print W9P, W space 9P. What does that mean? Resource temporarily unavailable. Man, right? I think that's E again. Resource temporarily unavailable. If I go up here, we're getting those on reads, yeah. So I got 14 out. Said, oh, this is just a previous eno value. So what I need to do is before any of this shit, I just need to say, hey, oh, sorry, not handle input. On the thread, we just need to set error node back to 0. and that'll fix that. So now make rerun over here and see write to 9 success. Print out state. I can then say block 9, block 8, block 9, print out. It's blocking. Send a bunch of garbage. And then here we say print unblock 9. I got a successful read. And then if I do some more here, okay. So that's like the basic IO server that I wanted to implement. It allowed me to establish arbitrary connections handled by threads, go in, block and unblock the threads from reading and writing, allowed me to send writes down like this. Yeah, I think that's pretty much all I wanted to implement with that. I know that went kind of long there. It's already 3 and I haven't gotten much reading done. But, you know, I'd rather spend time writing code here. Didn't mean to close out all that. Okay. I mean, this is already like a 233 line program, and I wrote most of it myself. Some of it I asked ChatGPT to write for me, but I definitely got a much better feel for how to coordinate like these threads and the sockets and the socket options and reading from their error states and doing all that. I think this is a good idea, setting up setters and getters that use the mutex instead of, you know, calling these functions independently. So all the all the data race prevention stuff is contained within the reading and writing here. This thing, yeah, that's fine. Okay. I don't like this because it does printf while it holds open the connection state. So I think it would be better if this was get sock state of FD like this. Yeah. And then we delete those and then just move these down here. So any reads and writes go through those 2 functions. And by doing it this way, we get printf out of the critical section. So the critical section literally is like reading from memory, writing to local memory. Reading from local memory, writing to global memory. They're just memory operations. That's good. Our handle calling goes in, it basically is a timeout, which is kind of like a jank way of like not blocking the reads. It then goes into an infinite loop. Based on its state, it'll take different actions. The default action is to perform a read. Again, the read's only going to take so much time, and then it'll reset. If it hit that counter, it'll get an E again here, in which case it'll just continue. If it was EOF, it returns the entire thing. So it stops reading and writing to the socket and cleans things up by returning here. It does not close the socket. I think we need to close the socket here. So maybe we say return. How do we do a label? Go to clean up like this. And here I'll just say go to cleanup. And then down here we'll say close of FD. Gotta close that side of the file descriptor. We'll just say closing FD %D FD here. There you go. So let's go ahead, jump to chapter 63. Oops, that's good enough. Make, and we'll run this. Go over here and see localhost. We got our handling connection 9. I'm going to say, hey, do a write to 9. That'll handle the write to 9. And then we'll do some reads over here. And then when this client goes away, it closes the FD on the server. If I print after that, I'm going to command 9. Oh, it's what is ASCII table 9? I think I need to say if there's nothing in the table, I need to have some indicator that there's nothing. It's an empty table, because that's like be better UI. So print socket state. Here I'll say socket state. And I would say puts. There we go. Make. And we'll nc, what is it? nc localhost. And if I do a p here, so it's connection state. Write to 2 and print. Sorry, write to 9 and print. Write to 9. Damn it. Write to 9. There we go. So I can say print, owner can't pp print socket state, and then if this thing goes away, so it's close FD, and if I do print, socket state is empty. Cool. It's a pretty nice little server. All right, that's just useful for me to test these different IO models out. So what I'm going to do is implement some servers that do the traditional blocking, non-blocking IO. And then we'll move on to the ePOL stuff. So basically the stuff that he's covered in the first couple first page here, I want to implement just to have examples of this is how you do blocking IO, this is how you do O-knob block, and then we'll iterate through the evolution of those. But now that we have this IO server done, I'm going to take a little bit of break because I've been streaming for 2.5 hours, so I'd like to take a little bit of a break here. Just a quick break, get some water and stuff and reset my brain a little bit. But when I get back, I'm going to start implementing on a blocking server, like a blocking threaded server. I think I can skip past like an iterative server. I think that's super basic. But yeah, start on like a threaded. So I'll add a to do here. Let's add to do. add we'll just do a threaded client, to be honest. So I don't even know if like we have an iOS server. It's threaded. It's doing this kind of like polling stuff. I'm trying to think. I kind of want to implement the clients using these concepts, because it doesn't matter if you're a server or a client. So we'll say implement threaded blocking IO client. Threaded non-blocking IO client. And then what was the other one that he discussed here? I think that was it. Yeah. Okay. We'll do those when we get back. So I'll probably take an hour break here. And then I'll come back and implement those two clients. And then we'll continue on the reading. Cool. All right. I will be back in about an hour.